Hey there, physical science kiddos. This is Mrs. O'Neill. I'm just going to be trying to deliver some of our instruction in a more traditional way, just so that this change in our situation isn't quite so severe. And so in addition to posting the notes online as a Google Doc or as a document, I'm also going to be just doing my usual read-through, just like I used to in the classroom, maybe with fewer interruptions. But, just in case you prefer hearing the notes instead of just reading them, or if you just want to listen to all the random nonsense I usually toss in, it'll still be just like that. And this way we can stay, hopefully help you guys understand the content better. So our last unit for the year is going to be about energy. The good news is the math for this is a lot easier compared to the math that we were doing with kinematics. There's still going to be some equations, but they're not going to be as complicated, and we're not going to be doing the big tables and stuff like that. A lot more of this is just general knowledge. We're going to be talking about things like light and sound and electricity and I think those are the three big ones. And heat. And today we're just focusing on heat. So today we're just about heat and temperature. So let's go ahead and get started. Oh, also I am doing this in just one run through. I don't have the time to make a bunch of videos and edit them. So whatever little weird glitches or random problems occur, I'm just going to leave in, just like in real life in the classroom. Sometimes things just go wrong. Just bear with me, and hopefully we can all just learn to work together. So energy. We've already talked about energy quite a bit in our last unit because we talked about kinetic energy, which is the energy of moving objects, and we talked about potential energy, which is that stored up ability to move. We talked a lot about people falling down the stairs. But now we're going to focus in a little bit tighter. The energy we're talking about in this unit isn't any different. It's still about moving objects or that stored up ability to move, but the objects involved are a lot smaller. And so we're talking about things like electricity, which involves electrons, or light, which is the motion of photons, or heat, which is the general motion of particles. They're all forms of energy, in particular they're all forms of kinetic energy because these are things that are moving. Electrons, photons, particles. They're just moving too quickly for us, or too fast for us to be able to see them. Today we're just going to focus on the heat side of that. So, when we're talking about particles and their motion, we're usually referring to temperature, because what we think of as temperature is literally speed, how fast those particles are going. The difference between hot water versus cold water is literally how fast the little water molecules are bouncing around. Hot water, the molecules are moving faster, and in cold water, the molecules are moving slower. But temperature is really just a measure of speed. But again, because the objects that we're measuring are so small, we can't just say it's miles per hour or something like that, even though it's really the same thing. Instead, we have special units. You've seen these before: degrees Celsius, degrees Fahrenheit, or K for Kelvin. Kelvin is probably new. Degrees Celsius and degrees Fahrenheit work out fine for our day-to-day uses, but they have this really irritating habit of going into negative numbers. You can have below zero in both Celsius and in Fahrenheit. And negative numbers are really bad for our math calculations, because then you get things like negative volume or negative number of moles, stuff like that. And it just doesn't work. And so we have to use a scale that has no negative numbers, and that's Kelvin. Because temperature is speed, the slowest possible temperature is not moving at all, when the particles are standing still. That's called absolute zero, and it's the bottom of the scale for Kelvin, and we just go up from there. So we can avoid that whole negative number thing. So just some comparisons here. Fahrenheit's the one that we grew up with. That's the standard used here in the United States. Basically not used anywhere else. So if we're talking to people from Europe or whatever, they're not going to understand our Fahrenheit numbers very well. But just to compare, freezing point of water is 32 degrees Fahrenheit, and the boiling part of water is 212. So there's a really big gap here. If it's 100 degrees Fahrenheit outside, it's a really hot sunny day, but you're not going to spontaneously combust. Celsius has smaller, or has bigger units. That's a big range. Each individual degree Fahrenheit is small. The range is smaller for Celsius. The individual degrees Celsius are bigger compared to an individual degree Fahrenheit. We set 0 as the freezing point of water and 100 as the boiling part of water. So if it's 100 degrees Celsius outside, you would not be going outside. That's like inside of your oven temperatures. An average day outside in degrees Celsius might be about 25 degrees. And your personal body temperature would be more like in the 30s, 36 or 37, something like that. Definitely not 98.6. If you are 98.6 degrees Celsius, your bodily fluids are close to boiling over. That would be very, very bad. Kelvin, since we have that no negative numbers, it turns out that the absolute coldest temperature possible is negative 273 degrees Celsius. And so we're going to call that 0 and count up from there. And so it's plus 273 Kelvin to get to 0 again for Celsius. So 0 Celsius is 273 Kelvin, and 100 Celsius is 373 Kelvin. A degree Kelvin is the same size as a degree Celsius. It just has a different starting point. We use degrees Celsius almost entirely in science because that's our metric unit, but if we need to avoid negative numbers, then we're going to switch to kelvins. Okay, now this is different than heat. We use them kind of the same. In our day-to-day lives, we tend to think of temperature and heat as more or less the same thing. Everything has temperature. Even objects that are entirely alone in the depths of outer space still have their own temperature. For heat to occur, you have to have more than one object because heat is an energy transfer from one object to another, specifically from the high energy, the hot object, to the low energy, the cold object. And without that transfer, there's no heat. So you always have temperature, but you don't always have heat necessarily. You might have a perfectly insulated object that's not gaining or losing energy, and there would be no heat occurring. In our day-to-day lives, though, we have lots of heat, too. We're always losing energy to our environment. Okay, the way that objects react to temperature changes can vary a bit. A lot of them increase in volume as they heat up. We call this thermal expansion. That's because in a solid, the individual little particles are locked into place, but they're still vibrating. And as you heat them up, they vibrate faster and faster. And that sort of stretches the bonds between the particles. The particles move out away from one another just ever so slightly. And when you're talking about billions and trillions of atoms, even tiny little distances add up. And so overall, the object expands. This is what causes concrete to crack, as an example, other than tree roots. That causes it too. But just the heat alone can cause cracks. If you've ever driven over a bridge or ridden in a car and ride over a bridge, it's got that sort of zippery area with those interlocking teeth. That's to allow the bridges to expand and contract as the temperature changes without breaking the concrete. And so thermal expansion is a thing that we sort of have to keep in mind. Materials also have what's called specific heat. This is how much energy is required to raise their temperature. Some things are very easy to heat up, like metals, for example. A metal spoon against a stove burner would get hot very, very quickly. Some things are a lot harder to heat up. Like if you're trying to boil water, you have to put that pot of water on the stove and just wait, because it takes a lot of energy to heat up water. Water has a high specific heat. So the definition here, the specific heat is the amount of energy needed to raise 1 gram of material by 1 degree Celsius. And there's a formula with calculations, but I went ahead and pulled that out because I figured we don't need to do a whole lot of math while we're all at home and our brains aren't working very well. And so I'm trying to simplify things a little bit. So no specific heat calculations this year, you lucky ducks. Okay, so how does heat move around? There's 3 different types of transfer. When 2 objects are in direct contact with one another, it's called conduction. This occurs when you touch things, like having a hot plate from the microwave or just hot water from the sink and you put your hand in it. If there's direct contact, that's conduction. The next way is called convection. Convection occurs when the particles can move and change location, and so it has to happen in fluids. Fluids is a category that includes both liquids and gases. As the particles are getting heated up, they're moving away from each other. That decreases their density and makes them float upwards. And so they rise upwards as they move, as you're heating them, and then as they cool off, they start to sink downwards again. We call this pattern, the up and down shift, a convection current. It's what you see when you're looking at a pot of boiling water and it's like bubbling over. The water is rising and sinking. This also creates like heat shimmers over a grill. It's the air density changing. Or that illusion of puddles on a hot highway is also due to the air density changes due to convection. If you hold your hand over a candle and you can feel the heat, that's from convection. Convection is always upwards, though, upwards and downwards. It does not go side to side. If you have heat transfer side to side without touching, that would be radiation, specifically through light or infrared. Infrared is part of the electromagnetic spectrum. It's a form of light. It's one that we detect as heat. Our bodies read it as heat. So if you're like watching a campfire and you're sitting out to the side and you can feel its heat, that's radiation, because the convection would only occur directly above a campfire. The sunshine on your skin is radiation. So it would be like radar and stuff like that. It can actually heat things up. They actually, when they first developed the radar imaging stations, they were trying to find like airplanes and stuff like that back in World War II. It was killing birds. Birds would fly into the radar paths and get cooked. And so that'd be a form of radiation as well, too. Nowadays, we don't let that happen because it was very sad. Okay, There are some laws that govern how energy is being transferred through and around our systems. For our homework, we're going to focus more on the heat and temperature definitions and also about our types of energy transfer, but I did want to cover the laws of thermodynamics at least a little bit, even though we're not going to spend a lot of time on them because they're kind of tricky and confusing. Okay, so there were 3 laws, but then I discovered that we kind of needed more definitions, and so they threw in a 0th law, which is silly, but they did it. And so the laws of thermodynamics are 0, 1, 2, and 3, not 1 through 4. So our 0th law, everything has energy and it can be measured. That's what I meant by definitions. Yeah, they're talking about energies, and then they realized they hadn't actually said that energy exists everywhere, and so they threw in the 0th law to make sure that that was really clear. Even things that aren't moving, even things that are totally alone, that don't seem to have a lot of activity going on, still have energy. Being made out of atoms means that you have energy. And so we can measure that energy when we look at its temperature or at its mass. So the first law is that of conservation of energy. We actually talked about this one in our last unit when we did the tables with potential energy and kinetic energy, and we summed up the mechanical energy and then did all the back calculations. We're not doing anything that complicated today. But the rule here is still the same. Energy is neither created nor destroyed. It just changes forms. Then our second law states that sort of defining heat. Energy flows downhill from the high energy systems to the low energy systems. Always. You can't force energy to go uphill. And then the third law is entropy. This one's really kind of interesting. Entropy is a measure of disorder. A system that has a lot of a lot of entropy is one that has a lot of chaos in it. And then one that has a low amount of entropy is one that's very organized. Everything's in its place. So we have a natural tendency here to become disorganized. I think of this in terms of like cleaning my room. If I never did anything at all to clean my room, it would eventually be a horrific mess. Cleaning my room takes energy, so we have to fight entropy to make the room clean again. But if you just leave it alone and let things just happen by themselves, entropy just happens. There's a natural tendency towards disorder. This has to do sort of with what we mean by organization. If we're talking about like like your room or something like that, when it's organized, everything is in its right place. And maybe some objects have more than one right place. Maybe your socks can go in, in a couple of different places, but it doesn't have an infinite number of right places. When it's disorganized, things are in the wrong places, and there are always more wrong places for things to be than there are right places. So it's just a probability game, really. If you threw a random basket of socks towards your dresser, they wouldn't end up all in your sock drawer all nicely paired up and folded. That would be cool, and that would be very much like Mary Poppins, but it doesn't happen. Okay, so natural tendency towards disorder. What this means is as we try to shift energy from one system to another, like turning electricity into light using a light bulb, we're losing some of that energy. We cannot have 100% efficiency. We lose energy as heat, as sound, as light. All of these things happen. Sometimes the energy transfers aren't very efficient at all. Like in a car, you're transferring chemical energy and gasoline into the forward motion of the car, the kinetic energy. Only like 30% actually transfers. The rest of it is lost as heat and sound and pollution and all sorts of stuff like that. Okay, that was a bit of a downer ending, but that's where we are. So that's the end of the notes for today. We're going to focus more on the electromagnetic spectrum tomorrow and Thursday and next Tuesday when we do notes again. I will be posting more of these videos as we go along. They'll probably get better. Right now this is still like very, very new to me, and I know it's new to you too. Please leave any questions that you might have on the comments on this assignment, and then don't forget to do the worksheet as well. Thanks and have a great day.